So now let's take one more step towards talking about functions. And what I want to do is I want to talk about the function f of z is z squared. And again, just to remind you about the notation, this means that our inputs are complex numbers and our outputs are complex numbers. This does not guarantee that every complex number is an output, although in this case it will be. So it turns out that every complex number can be written in the form z squared for some complex number z. And this is a fact that we actually already proved in one of the first videos, right, is that every number has a square root in that certain sense. So the function f of z equals z squared, by the way, I just want to be clear with my notation here. If I write f of z as z squared, then what you can do is you can also write this as z gets mapped to z squared. I will try to use the f of z equals z squared notation, but just if you see this, this means the same thing. We're talking about the function that takes z to z squared. Okay, and so that's what that is. So this extra line here means that this is assigned to the complex number z gets assigned to the complex number z squared. What I want to do is I just want to start playing around with this function. I don't want to do anything too serious right off the bat. And I want to think about if I were to take some points here. So let's say I were to take the point, we can do some kind of boring examples. Let's say 0 and 1 and I and minus I, and then maybe we'll do 1 plus I. So let's give these some colors. So here this is 1 plus I, and 1 and I and minus I. Okay, so minus I, oops, I should have saved the colors, I and 1. Okay, and we'll leave the boring old origin just blue. Now, let's think about what's going to happen for all of these values. Okay, so what I'm going to do is I'm going to draw a table, and I'm going to think about our value z versus our value z squared. Okay, so let's do that. So let's make a little table, and if we were to take, some of these are really straightforward. If we were to take 0, 1, I, minus I, 1 plus I, let's think about what happens. Okay. Well, 0 squared is 0, nothing interesting there. 1 squared is 1, again, nothing, dare I say, nothing interesting there. 0 and 1 are what are called fixed points. These are the only complex numbers that don't get moved under this transformation. So they're called fixed points of this function. If we were to take I and square it, we would get I squared, which would be minus 1. Likewise, if we were to take minus I and square it, we will get minus 1. And then the only one that's even a little interesting so far is 1 plus I. And if we were to take 1 plus I, let's think about what would happen here. You would end up with, you would end up with 1 plus I squared, which would be 1 squared plus I squared plus 2I. And of course, I squared is minus 1, so this will just be 2I. And so let's copy the graph that we have here, and I just want to think about how this is going to work. In general, when you're talking about a function, so I think this is worth just stepping back for 1 second. When you talk about a function like f mapping the reals to the reals given by f of x equals x squared, you can think of the function as a picture, right? This is kind of something that's so innate in what we do, but I want to think about how this works. The input is a one-dimensional line. It's f of, we're thinking about the real value, and all the values that we're allowed to plug into this function, f of x equals x squared, are just all the real values from negative infinity to infinity. And then what we do is we think about what's the output that this gets mapped to. So we would map 0 to 0, 1 to 1, 2 to 4, negative 1 to 1, and so on. And if you fill this out, you end up with this nice, smooth curve, right, that we know and love as the parabola. Okay, and so that's what that is. And you can think of the graph of the function is kind of this two-dimensional object, right? It's this thing that you can draw on paper. It's this two-dimensional thing. And that's because the inputs are one variable and the outputs are one variable. In complex numbers, you can't draw such simple pictures anymore because your inputs are two-dimensional and your outputs are two-dimensional, and therefore you're going to have a four-dimensional graph. And so there's no one nice way to represent this four-dimensional graph. There's two ways. And one way is to talk about what's like I'm doing here. You can kind of assign each point a color, and then you can take, and that'll give you a two-dimensional graph. And then you can look at the two-dimensional outputs, and you can see where did all the colors get to? Where did they all get moved to? And that's one way to do it. Another way to do it is to think about the real and imaginary parts. And so you can think of your inputs as your x and y values, and then your outputs are going to have, again, two coordinates, whatever you want to call them. And you can think about where do your x and y values map to the real part of the function, and where do they map to the imaginary part? And therefore, another way to think about complex graphs is you can think of two three-dimensional graphs. And the first graph would be f of xy gets mapped to, so the point xy gets mapped to the real part of f of xy. And then the second graph would be the point xy gets mapped to the imaginary part of f of xy. And since those are both, since the real part is one-dimensional, then that graph is three-dimensional itself because you have two dimensions of inputs, right? You have your x and y, and then you have the real part of your output, which is your third dimension. So you could think of it as a three-dimensional graph. And then likewise, the imaginary part will be the same three-dimensional graph. So you have two variables for your inputs and then one variable for your outputs. You have a three-dimensional graph that way. So there's two ways to kind of talk about complex graphs. You can do what's called domain coloring. So you can color each point and then see where do the colors get mapped to. That's the picture that's actually on canvas, is the domain coloring of some particular function. It doesn't matter what the function is. So you can do this coloring trick, or what you can do is you can do the two three-dimensional graphs. But even the two three-dimensional graphs, they tell you a little bit in that they tell you what's the real and what's the imaginary part of your output, but it's hard to kind of put them together and think of one function. So I tend to favor the graph coloring method. So let's just see what's going to happen here. So these are our inputs. Okay, so this is our values z. And then they're going to get mapped to z squared. So these are going to be our outputs. And we talked about where these get mapped to. We know that 0 gets mapped to 0, so that's boring. 1 gets mapped to 1, also boring. We know that I and minus I get mapped to -1. So I is there, minus I is there. That's a slightly different color if we can zoom in on that. And then the only other point that we looked at was 2i. I'm sorry, it was I plus 1, which gets mapped to 2i. So that's something like up here. Okay, so that's 2i. So that's what that graph looks like, just to talk about a few examples there. One other thing that I think is useful is if we think about this in terms of geometry. If I were to pick some ray starting at the origin and then just going as far as you want, or maybe a line segment, it doesn't matter if it's infinite or not. If you were to have some line segment or some array starting at the origin, when you multiply two complex numbers, remember that there's a geometric description of what's happening. And that geometric description basically comes from Euler's theorem, Euler's identity, although we didn't say it at the time. What you do is if you multiply two numbers, you add the two angles, or you add the two arguments together. So in our case, if we were to start with the angle theta, your output would have the angle 2 theta. And then the line segment that you're talking about, whatever that is, gets stretched to a line segment that's the square of its length. So if this is length r, then this is length r squared. Okay, and so that's what the graph f of z equals z does to these line segments. I think the last thing to do here is to before I show you some pictures, I think the last thing to do is to think about what happens to, instead of talking about line segments starting at the origin, let's talk about horizontal and vertical line segments. So if you were to consider, say, the line segment that's something like this. So it's some specific fixed x value, say x naught, and then the y values are free to be whatever you want them to be. Let's think about what would happen if we were to map this x naught plus iy under this function. We will get x naught plus iy squared, which would be some constant squared minus y squared plus 2i x naught y. And so this is what would happen to the horizontal line, is that it would get sent to basically a parabola. And the parabola that it gets sent to, we just have to think about this for a second. This is a constant, so it does change what the parabola is, but it doesn't change the general shape of it, right? It might just move it a little bit, in one direction. Maybe it moves over like 5 points or something, but it's not going to change the general shape. Likewise here, this factor is not going to determine which shape it opens and so on, like which direction it opens or anything like that. But let's think about what I just said. This bothers me. What I just said was slightly incorrect. If x naught is negative, it will affect which direction it opens. And if x0 is 0, then that also changes the way it is. But in general, it's not going to change the generic shape of it. So if we think about this, this vertical line is going to get mapped to a parabola, because what's going to happen is you're going to think about, you have minus y squared and y, and that's kind of like if you were to have the function x equals, so if you were to have, instead of thinking about y equals f of x, you'd have x equals f of y, where you would have x equals y squared, something like that. And in this case, it's actually minus y squared. And again, I'm ignoring those constants, x naught, they don't really matter for this discussion, but they end up with these kind of parabolas that get mapped to. So you can think of the output of this function on these vertical lines. These vertical lines get outputted to parabolas, and they're parabolas that are going to open up like this. They're going to have the general shape x equals minus y squared, something like that. Okay, and so again, these are going to shift that value a little bit, so they're not going to be right at the origin, but that's going to be what that function does for us. I'm going to leave it to you to figure out what happens if you were to look at, say, x plus I y naught. Okay, so I will leave that to you to figure out exactly what happens there. But the last thing that I want to do is I want to show you a picture of what's going to happen here. And so, oops. So what I want to do is I want to show you the graph. Here we go. So I want to show you, this is the graph, and this is using software. So just to tell you where I got this is using software called 3D Explore Math, which is an app developed by a pair of mathematicians at Brandeis University. And so this is the function f of z equals z squared. Okay, so f of z is z squared. And you can see that what I was saying before is true, where these lines, these yellow lines, they get mapped to these parabolas, right? You get mapped to those parabolas. And so I'll let you work out how the other part works. But the one thing that I really want to focus in on this example, the one thing I really want to focus in on is that these are examples of what are called conformal maps. Now, conformal maps, that's a topic that we'll talk about in some detail soon. But the key feature in a conformal map is that if you have a pair of lines, or actually if you have two paths that intersect at a certain angle, and then you apply a conformal map to those paths, then their output also intersect at that same angle. Okay, And so, for example, here, if you were to zoom in on one little part, you could look at, say this region here. And you can think of the horizontal and the vertical parts, they're intersecting at 90 degrees. And so you want to figure out where do the yellow and where do the really light blue curves intersect. And that would be, it's kind of tough to tell here, but that would be somewhere around probably this intersection. And so if you look at it very carefully, it turns out that before the inputs were at 90 degrees because they were grid lines, and the outputs also happen at 90 degrees. And so this is an example of what's called a conformal map. And again, conformal, if you want to, just an intuitive way to think about it, conformal just means angle preserving. Whatever angle you have of two paths that intersects, if you were to apply this map, you would get out two different paths, but they have the same angle of intersection. Okay, so this is an example of what's called a conformal map. So this is f of z equals z squared.